In this section, we are going to construct an action for the gravitational field. We are going to find an action for the gravitational field coupled to matter as well, and we are going to derive the equations of motion corresponding to that action, which will be the Einstein equations. The first thing that we have to do, according to the principle of general covariance, is to construct this action for just the gravitational field. So it will be an action that only depends on the metric, and that will be some integral of some Lagrangian density depending on g, derivatives of g. Okay, I don't know how many. This is something that we are going to discuss. But in principle, no other field. Okay. According to this principle of general covariance, since this action is going to be invariant under general coordinate transformations, what we have to do is to use the diff invariant volume element, which means that we have to consider a Lagrangian density such that when it is divided by the square root of the determinant of the metric, gives something which is strictly invariant, a scalar. Now, what kind of scalars can we construct out of the metric and its derivatives? Well, turns out that the only thing is given that the covariant derivative of the metric, because we want this L to be built out of tensors, maybe with contractions, and this will give us scalars. Then the only tensors that we can construct from the metric, given the fact that we are using a metric compatible connection, okay, turn out to be the Riemann tensor, and whatever tensors I can construct by contracting indices or contracting several curvature tensors and so on. For instance, you know that from the Riemann tensor we can construct the Ricci tensor just by identifying these two indices and summing over them, and we can also construct the Ricci scalar. Okay, this would be one of the possible invariants that we can use. But we can also do more things. We could, for instance, it would be easier to use r squared. It is also a scalar, or in general, any function of r. This theory is constructed with this Lagrangian are very popular nowadays, and they are they are a particular case of what are called now modified gravities. Another possibility is to take the Ricci tensor, okay, and then construct this scalar and consider powers of it, or things like that. And then with r mu nu itself, you can construct, for instance, this scalar, which is called the Kretschmann invariant. And of course, you can multiply one scalar by another scalar, this times this or times that. There are many possibilities. However, we know that the theories that contain derivatives higher than 3, equal or higher than 3, so higher than 2, in general lead to pathologies. So on general grounds, we want to avoid that, and we are going to consider only Lagrangians that only contain 2 derivatives. So this kind of thing is allowed. This kind of thing is also allowed because the difference is a total derivative, so they are kind of equivalent. But other invariants, okay, in fact, you know that the Ricci tensor contains this kind of terms. Okay, let me remind you that the Ricci tensor, the Riemann tensor contains terms of this form, antisymmetrized, and terms of this form. Now, gamma, being the Levi-Civita connection, is determined by the Christoffel symbols, and these are of this form. Okay, schematically. So if you have two of these, you get terms with dg like this, and if you have something like this, then you get terms of this form. Okay, so both of them are contained in the Riemann tensor and are contained also on R mu nu. Okay, it's just the Riemann tensor with two indices contracted, and are contained in the Ricci scalar. However, anything which is of higher order in the Riemann tensor contains, by this reasoning, higher derivatives of the metric and will be pathological. Taking into account all this, basically you are left with only one possibility, and this possibility is that L divided by the square root of G is R. Okay, up to constants that we will have to determine later. This action that contains R, okay, is called the Einstein-Hilbert action. We will denote it by this. This is the action that Hilbert constructed, and from which he derived the Einstein equations that Einstein himself derived finally shortly before Hilbert in the right way. Okay, he derived some other equations, he proposed some other equations which were inconsistent a bit earlier than that. There has been some controversy on whether the correct Einstein equations were really found by Einstein or Hilbert first, but okay, this is a matter for the historians. I will not get into that. What is important here, or I think is relevant, is that it is extremely easy to arrive to this action just based on the principle of general covariance, counting derivatives, and okay, there is essentially this one possibility only. Okay, there is one possible additional term that we will discuss later, and which has associated a very big controversy, but let's just focus on this single term for the moment. And the next thing that we have to do is to determine this normalization constant C. And first, it is good to write what are the dimensions of the C, taking into account everything. So you know that dx4, d4x, sorry, has dimensions of length to the fourth. The metric is I-dimensional, so you know that this has dimensions of L squared. Okay, the metric is A-dimensional, and these have dimensions of length only. Okay, so this is L and L, and this makes this equation consistent in terms of dimensions. So square root of G is dimensionless. And how about R? R, well, we just saw here that it has it is given by this. The metric doesn't really count. Gamma contains first derivatives, so it has dimensions of L minus 1. And this has dimensions, gamma gamma has dimensions of L minus 2, and partial gamma has also dimensions of L minus 2. So this has dimensions of L minus 2. This implies that, okay, what are the dimensions? What should be the dimensions of the action? Well, this has dimensions of action. Remember that these are the same dimensions of angular momentum, and in fact the same dimensions as the Planck constant. Okay. So sorry, before I do this, so suppose that I know that this divided by h bar, okay, should be dimensionless. if it is to be dimensionless, this C, I call it C prime because now it is divided by h bar, must have dimensions of L minus 2. Now, in this C prime can contain the Newton constant, can contain the speed of light, and could also contain h bar itself. But it has to have dimensions of length 2 minus 2. Now, you know that there are unique combinations of these three constants of nature, G, C, and h bar, that have dimensions of length, time, and mass, and these are called the Planck length, Planck time, and Planck mass. So the natural thing would be to use the Planck length square, okay, or the inverse of the Planck length square. So what is the Planck length? The Planck length is given by h bar Gn, the Newton constant, divided by C cube. Okay, so C prime should be 1 divided by, or let's say this should be given by something like this, up to a normalization constant which is conventional and which is usually chosen to be 16 pi. Okay, so the C prime is actually 16 pi LP squared. So if I write everything together, I think here the important fact, of course, is that when you divide this by h bar or you use natural units, anything like that, the C prime is just the length, the Planck length to the minus 2. Okay. And if you work in higher dimensions, and well, R is always L minus 2, the dx should have dimensions of L to the d, and this would be, the constant would be 1 over the Planck length to the d minus 2, to the power d minus 2. So let me just rewrite the Einstein-Hilbert action. Now not divided by h bar, okay? This is just C cube divided by 16 pi times the Newton constant, the for x square root of g r. Okay, and remember that if I divide this by h bar, okay, I get oops, there is here, this is the Planck length square itself. Okay, sorry, not the Planck length. The Planck length is the square root of that. So if I divide this by h bar, the Planck length square arises naturally as the normalization constant up to a conventional normalization factor. Another constant that is used okay, in natural units is the Planck mass, and this is a relation that we would like to have. So this is the Planck mass divided times C and times divided by h bar. In natural units, LP is just the inverse of MP, the Planck mass. And typically phenomenologists of people who study beyond the standard model physics tend to use the Planck mass instead of the Planck length, which is favored by people who are more focused on geometry or the quantum gravity part. Because if you are doing beyond the standard model phenomenology, you want to compare the masses of your particles with the Planck mass. That is the natural thing to do, and not with the Planck length, although these two things are very closely related, as we just see. Okay, just one word of warning. The action looks extremely simple, but R is highly nonlinear in the metric. It contains inverse metrics multiplied by derivatives of the metric. There is a second derivative of the metric. So all these things that we don't usually see in a theory as simple as d phi squared, okay, which is really considered a free theory, are represent self-interactions of the gravitational field with itself. And you can show, and we will see a bit of this when we study the weak field expansion, that you can understand these couplings as, for instance, the coupling of the gravitational field to its own energy momentum tensor, which is what you expect. As I said, there is no true energy momentum tensor in general covariant sense, but there is an energy momentum tensor, an approximate energy momentum tensor, which is good in the weak field approximation, so in a sort of Minkowskian limit. And then in that case, you have a conserved energy momentum tensor, well, an energy momentum tensor, which when you add to it the energy momentum tensor of the matter fields is conserved, this total energy momentum tensor. But from this covariant perspective, you cannot see an energy momentum tensor. However, you somehow know that it is here. This tells you that the principle of equivalence in its strong form may be obeyed, and this is the case in general relativity. We didn't ask for it, but it turns out that it is completely natural, that somehow the principle of general covariance implies the strong equivalence principle. Well, you have to prove not just that that gravity couples to the energy momentum tensor of gravity, but that it does so with the same strength as with the rest of the energy momentum tensor of the matter fields. But you can do this, okay? So even though we didn't want to, or we didn't aim for it, turns out that the principle of general covariance has led us to a theory that preserves the strong energy equivalence principle. And now that we have an action, the next thing to do is to find the equations of motion. Okay, we will just consider this part because we know what is the contribution of to the total equations of motion when we add matter fields. This is what we have studied exhaustively in the previous video. So let's try to do this not using the Euler-Lagrange equations, because really in this case they are not so useful. You have to find the derivatives with respect to the metric, but you have inverse metrics all the time. It's really very messy if you try to do that, and the result is not evidently covariant. Okay, you have to compute a long time, and then you will manage to write it in a covariant way. If you vary the action, you get the right result in a much shorter time. So let's do this. Okay, we want to vary this Einstein-Hilbert action. We don't care very much about the proportionality constant now. And now this variation is a variation of the fields with the standard boundary conditions and so on, only contains these two terms. The first term we have, we know what it is. We choose to vary with respect to the inverse metric because it will be simpler. We know that is the variation of the square root of the metric gives you minus a half of the square root of the determinant of the metric times g mu nu delta g mu nu inverse. Okay, and all these times r. Then plus the square root of g, and remember that r is g mu nu r mu nu. So we have delta g mu nu r mu nu plus square root of g mu nu delta r mu nu. Okay, let me collect the terms that are immediately proportional to delta g mu nu. And these are, okay, this is the square root of g, which is a common factor. And then we have r mu nu minus a half of g mu nu r times delta g mu nu. But then there is another term, which is g mu nu delta r mu nu. Okay, before I go on and compute this delta r mu nu, let's notice that this combination is what we define as the Einstein tensor. Okay, and now let's try to compute this delta of r mu nu. But before I compute delta r mu nu, I will just compute delta of r mu mu alpha beta, so the full the full Riemann tensor, because I'm going to derive an identity which is very useful, and the only difference between the variation of the Ricci tensor and the Riemann tensor is that now I will have to identify two indices, so I can derive one from the other very easily. Okay, so this is by definition the variation of partial derivative of this plus, okay, sorry, gamma nu alpha rho minus what I get by interchanging mu and nu in the previous terms. Okay. As I said, we are very lazy people, theoretical physicists. Now, the first thing that you realize is that r mu nu, okay, only depends on the connection, not on the metric explicitly. It depends on the metric only through the connection. This is why varying the Riemann tensor is useful. Okay, if we had chosen to vary with respect to the metric instead of the inverse metric, here we would have g mu nu delta r mu nu, but okay, this depends on the metric and on the connection. So this, well, it's just a bit more complicated. It's not so natural to do that. So this is why I do it in this way. And now there are two terms, gamma mu rho beta mu alpha rho plus gamma mu rho beta delta gamma nu alpha rho. And let me also write the other two terms, the ones that I find by interchanging mu and nu and with opposite sign. So this is just delta mu alpha beta minus delta gamma nu rho beta gamma mu alpha rho minus gamma nu rho beta delta gamma mu alpha rho. Okay, then let's collect, well, this term is associated to terms that have gamma mu, because they also have this delta with gamma nu. Some other indices may differ, but okay, it is clearly related to this one and also to this one. Okay, both of them have gamma mu and something else and delta gamma nu rho beta, while this term here is related to this one and this one. Let me put this in order. What I get is alpha beta, and then I set this term plus gamma mu rho beta delta gamma nu alpha rho minus gamma mu alpha rho delta gamma nu rho beta, and here terms that I find by interchanging mu and nu, alpha beta minus gamma nu rho beta delta gamma mu alpha rho plus gamma nu alpha beta delta gamma mu rho beta. Now you see that this is almost, the first line is almost the covariant derivative of delta gamma nu alpha beta, but there is one term missing because well, this time takes care of the upper index beta, the contravariant index beta. This one takes care of only one of the covariant indices of the alpha one, in fact. So what I'm going to do is add by hand the term that I need to rewrite this as a covariant derivative. Okay, and this is rho alpha and beta, and if I have subtracted it here, I add it here. Exactly the same term. And now if I look at the second line, I see that I also have the covariant derivative with respect to nu of what I have of delta gamma mu alpha beta. Since the second line is really what I get from the first line by interchanging mu and nu, and this is true because, okay, if I interchange mu and nu and I change the sign, this is precisely what I get, okay, because gamma mu nu is symmetric. In fact, this is, I don't need to check too much, this is just nabla mu of delta gamma nu alpha beta, and the other line gives me gamma nu delta gamma mu alpha beta, or in a more compact form, 2 times the antisymmetrized covariant derivative. Okay, this is the result, and this is called the Palatine Identity. And probably you are scandalized that, because I have insisted so much on the fact that gamma is not a tensor, that now you see me writing a covariant derivative of something that doesn't look like a tensor. But you see that any the variation of the connection is a tensor. It is a difference between 2 connections, okay, one in some one connection for one metric maybe, and the other for another metric that differs on the delta G. And the fact is that both of them transform they transform in the same way, of course, but the inhomogeneous term of both of them is identical. That's the point. And then they cancel. So the variation of the connection transforms as a tensor. So gamma is not a tensor. Oh, it is a connection, which is something else. But delta gamma is a tensor. And then it makes sense to define the covariant derivative of delta. Okay, so now using this, I can find the variation of the Ricci tensor. Better with these indices because the only thing that they have to do is to call beta nu in this expression. So I get nabla mu delta gamma nu alpha nu minus nabla nu delta gamma mu alpha nu, and this is the result we need. Okay, we can just replace this delta arm nu here, and let me just consider this term. So delta G mu alpha, G mu alpha delta R mu alpha minus G mu alpha nabla nu delta gamma mu alpha nu. Then of course we can take the metric inside of the covariant derivative. Okay, and this term we can do exactly the same. Now these 2 terms are scalars, so they are really covariant divergences. But in one case we're using the index mu here, and the other case the index nu. So to make evident that this whole thing is a total derivative, what I'm going to do is to call this mu, and mu I call something else, I don't know, rho. Okay, that this is alpha, so this is just nabla g mu alpha delta gamma nu alpha nu minus g rho alpha delta gamma rho alpha mu. The conclusion is that we just proved that this term is a total derivative. Okay, then now the question is, can we make or can we show that this total derivative vanishes using the boundary conditions delta g mu nu on the boundary equal to 0? Well, the answer is no. And the answer is no because when you vary the connection, you will find terms which are of the form delta of derivatives of g, not just delta of g. And the only way to set that to 0 would be to impose conditions also on the variations of the derivatives of g, which is really not allowed in this variational problem. You have to do something in order to cancel this total derivative, and this something, although Hilbert really ignored this problem, okay, somehow he said, okay, this boundary term will not contribute, this is not a relevant part, and probably he only cared about the equations of motion that you can derive, which are given by the other term. So he just used the action as a device to find the equations of motion. Well, maybe 50 years later, Hawking and Gibbons and York independently realized that if you want to evaluate the action, if you really care about the value of the action, and we know that the action is important if you want to compute Feynman path integrals or for other purposes, not just it is important for many other things, and not just for deriving the classical equations of motion. In that case, you have to do something, and this something that you can do in order to make this variational problem fully consistent without imposing conditions on the derivatives of the metric on the boundary, what you have to do is to add to the Einstein-Hilbert action a boundary term which is called the Gibbons-Hawking-York or the York-Gibbons-Hawking term. Okay. It is a boundary term, means that it is a total derivative, and this means that it doesn't modify the Einstein equations, which would be unacceptable probably because they work very well. However, the variation of the terms of this term cancel precisely the unwanted terms that you have in this total derivative. So you can formulate this variational principle in a more rigorous way that I'm doing here. So I will not get into all that, but you have to know that this term is troublesome, okay, and you have to deal with it in a special way in order to show that it doesn't contribute and so on. In any case, after you do this, you realize that the conclusion is that if this boundary term does not matter, you get rid of it by some way, using, for instance, this Gibbons-Hawking-York term. The equations of motion that you derive from the Einstein-Hilbert equations, and this is what we were after, are this. Okay. If there are no matter fields, clearly you conclude, okay, there is this constant here, okay, not divided by h bar, so it is just c. But if there is no matter, these are the vacuum Einstein equations. So, and here vacuum means that in this context that there are no matter fields. They are the only field which is present is the gravitational field. Now we can check if the property that we knew the equations of the gravitational field had to satisfy are indeed satisfied. Okay, and remember that general covariance of the action implied that the divergence of the equations vanishes off shell. So this is really an identity, not a consequence of the equations of motion. Well, in this case, if these are the equations, you have this, because the square root of g can go through the covariant derivative, and you know that this is 0 automatically and without any use of any equations of motion, because this is the content of the contracted Bianchi identity. This is good because, well, it tells you that everything is consistent, and you expected that it had to be this way. Finding the equations of motion from an invariant action ensures that you are going to get this property. And now let me show you how you could have made something wrong, just like Einstein did. If you are just looking for equations of motion for the gravitational field, which are most of second order in the derivatives of the metric, which are also symmetric, probably the only possibility, or the simplest possibility, is not g mu nu equal to 0, but r mu nu equal to 0 in vacuum. In fact, well, let me make it this better. What Einstein proposed was that this was up to some constant. Okay, in presence of matter, this is what you could have. You know that from this, if you have matter, after all the discussion of that we had in the previous video, you know that the equations of motion will be g mu nu proportional to t mu nu. Wait, this is down, evidently. Well, the difference is that if I try to check, so try to take the covariant divergence in these two sides, I know that this is different from 0 in general, which means that this will be different from 0 in general. But I know that this has to have a special relativistic limit when g is replaced by eta, which is this, and this is just not satisfied. Here I know that, well, I am repeating what I said in the previous video, but it is so important. Okay, I know that this is automatically 0, so I know that this is automatically 0. Okay, and this indeed reduces in the special relativistic limit to this high consistency. Okay, so this works and this doesn't work, and you get the right equations from an action, and if you try to guess the equations, well, you fail. Einstein realized that this was not consistent, and he had to modify the equations of motion that he proposed at the beginning. And this modification was to replace r mu nu by g mu nu, because this g mu nu satisfies this contracted Bianchi identity. Hilbert didn't have to work so hard. He just took the action and found consistent equations right from the beginning, and this is why we are using this approach in this course. Now, before we start studying the coupling to matter fields, if you remember what I said before, it was not so long ago, so you may still remember it. When I said that the only candidate for the Lagrangian was R, I said, well, there is another possibility, but we will discuss this later. Okay, there is no other possibility if you just think of a dynamical term, because it has to contain some derivatives in order to have dynamics. But now that you have a dynamical term, because these equations, okay, already have dynamics, you may think on the other term, but because it could be added. What is this term? Okay. What can I add to this Lagrangian? So R is a scalar. What else can I add? Well, a constant. Clearly, a constant satisfies, it is really invariant. Okay, it's a constant over all the space-time. This constant is normalized in this way, and this is called the cosmological constant. The fact that Einstein did not include this possibility in his first version and then only did it when he was unable to find a static universe with only this term R, and then he thought, okay, maybe if I add something else. Okay. Well, all this makes this cosmological constant a very controversial term. However, it is very natural. From the field theory point of view, it is natural to include all the terms which are compatible with the symmetries that you have. So this is a natural term that there are no reasons to exclude. The only reason to exclude it is that you could try to measure it, and you may find that it is zero, that it vanishes in nature. That's a possibility. However, as you know, people have determined that lambda is different from zero. It has a very, very small value, but it is different from zero. And okay, I don't think there is a controversy in this respect anymore. But the controversies arise from another point of view. And let me just show you. Let's find the equations of motion. It is almost trivial to find that now you get an extra term. Okay. Now I include with C equal 1 16 pi G, and you have G mu nu plus G mu nu lambda. Okay, and then you may have matter. Let's write the matter contribution to this equation, and all these equal to 0. Then, okay, I can rewrite this in this way. And okay, but I could also write it in a different way. You will, well, it is the same equation, but remember that when we write things on the right or on the left hand side, we are trying to say that we view those terms as fields, or as radiation fields, and matter field sources. So if I write the equation in this way, okay, this is one way of presenting the problem. If I write the equation in this way, I am basically saying that lambda is a sort of matter. In fact, as we will see, we can view lambda or this term as the energy momentum tensor of a fluid with some very peculiar properties, but we can view it like that, and we can associate this lambda to that fluid, so some kind of matter or energy which is in the universe and that we may not know. This is the term that, from this point of view, this is what is called dark energy. So dark energy manifests itself from this point of view as an additional term in the energy momentum tensor of matter. From this point of view, however, what you are saying, although the calculations are exactly the same, what you are saying is something different. You are saying that lambda is a property of our universe, of the gravitational field, to be determined experimentally, but well, just like the Newton constant, okay? It's a characteristic of our universe that we still don't know how to predict or how to explain in terms of something more fundamental, but it is that. It is not to be viewed as a fluid filling the universe. Okay. If you think of lambda in this way, then you will spend a lot of time finding candidates that you can understand in some way as energy whose contribution is identical to this lambda or similar in some time of the universe. If you think of the cosmological constant in this way, well, you will probably proceed in a different way. You will wonder why our universe has this lambda for other reasons. Okay, but this makes a difference on your approach to understanding this lambda, although I insist that the calculations are the same. On the other hand, since now the equation of motion of the gravitational part is just this, observe that the property that the covariant divergence of this is 0 still holds trivially. Okay, this is 0 trivially because of the contracted Bianchi identity, and this because this is a constant and the metric is covariantly constant. Okay, so it is as simple as that. In the case in which the matter tensor is 0, so there is no matter, in the vacuum case, and you see now that vacuum means nothing different in presence of a cosmological constant. So some people would call really vacuum when there is no cosmological constant either. Well, you can try to simplify the equations that we have obtained. Okay, and you can do this by taking the trace. Taking the trace means multiplying by J mu nu. Okay, you can see this in this way. You first multiply this matrix by some other matrix, and now taking the trace means summing over mu and alpha. So you just write mu, which obviously is equal to mu. Now remembering that G mu nu is capital G mu nu is R mu nu times G mu nu. This gives you R minus a half, and then you have G mu nu in 4 dimensions. This is 2. 4 in 4 dimensions. It is the trace of delta plus 4 times lambda. This is equal to 0. So this is minus 1R. So R is equal to minus 4 lambda. Oops, sorry, plus 4 lambda because it was minus R equal to 4 lambda. Now we can replace R back into these equations, and this gives you R mu nu minus a half G mu nu, the value of R, which is 4 lambda, and this equal to G mu nu lambda. This gives you minus 2 G mu nu lambda. You put it in the other side, and what you get is sorry, this is minus. Okay, it was plus here. This gives you G mu nu lambda. So in vacuum, the solutions of these equations, which are sometimes called cosmological Einstein equations, reduce to equations that satisfy this property. Okay, which is a very this is a very interesting equation. Spaces that satisfy this equation are called Einstein spaces. Okay, I have used the fact that we are in 4-dimensional space, and this is because the normalization of this term here has been cooked precisely to get this equation with no extra factor in exactly 4 dimensions. If you were in d dimensions, okay, forgetting about the fact that this constant should change, okay, it should be something else. But then what you have to write here is d minus 2. And then you arrive to the same equation with this normalization, and you also get, just taking the trace of this, you recover r equal to d, now lambda. These two equations, and well, this is enough to find this, and then you can reproduce the original equation. So you only need to worry about this one. The last thing to mention about the cosmological constant is that, of course, it is a constant. The value is important, but something which is perhaps even more important is the sign. Now, there are two possible signs. One is lambda larger than 0, at least in these conventions. This is called a de Sitter-like cosmological constant. Well, and why? Because remember these two solutions that we constructed, finding the induced metric of a hyperboloid, of some on some hyperboloid. Okay, one of them was called de Sitter, and the other one was called anti-de Sitter. So de Sitter space is that metric is a solution of these equations with lambda positive. Lambda negative is called anti-de Sitter. Okay, and the space that we called anti-de Sitter is a solution with lambda negative, and this lambda is related to this radius. In fact, if you look at these equations, okay, I didn't mention what were the units of lambda, but if r has dimensions of length to minus 2, then lambda has dimensions of L to the minus 2. Sometimes people write, instead of lambda, 1 over L squared, where this L is some length scale that you have in your theory. Maybe you can put it also say it in the other way. Lambda introduces another length scale in your theory apart from the Planck length, which is already included just explicitly in front of the action. Okay, this is true in any dimension because R has the same dimensions of length to the minus 2 in any dimension. So if you remember, there was a parameter R in the way we constructed the de Sitter and anti-de Sitter solutions. Of course, this R plays the role of L. Okay, so these two things are the same. Finally, well, we want to study the complete Einstein equations with matter. Somehow I already wrote something here, okay, but let me just tell you how I found that, although with all the explanations that we have given in the previous videos, you should already know. You have the complete action, okay, contains is an action for gravity and matter fields in interaction, and in general relativity, which is the theory that we are constructing here, this action contains two terms. One is the Einstein-Hilbert term, and the other one is the matter term, which depends on phi, but also on g because of the principle of general covariance. You are forced to introduce g. Okay, but maybe you have boundary terms that we don't care about, and if you vary this action after all the discussions, you know that this is going to give you 1 over 16 pi g times g mu nu. Okay, and this is going to give you minus a half of t mu nu matter. Okay, and the equations tell you that this is equal to 0. This matter energy momentum tensor depends on phi and on g, And now you write this in the standard way. You get this, which are the Einstein equations. Now the complete ones, not just the vacuum Einstein equations. Okay, as we have advanced, I mean, anything that you write in this form will act as a source for the gravitational field. Okay, and this is the source for the gravitational field. Of course, you can also vary these equations with respect to phi. Okay, the general variation contains variations with respect to G mu and also variations with respect to phi. This gives you the equations of motion of the matter field. If it is a scalar, remember that it was minus a square root of G nabla squared phi equal to 0. And the whole setup, the consistency that you have to remember, because I think it is very important conceptually, is that if you now take the divergence of both sides of the Einstein equations, okay, you get this chain of relations. This is 0 because of the Planck identity. This means that is always 0 identically. Now this is equal by virtue of the Einstein equations, which are equations of motion. This is equal to 8 pi g, and now the divergence of the mu matter. And as we have shown, okay, because of the Netter identity, and this is an identity that holds off shell, this gives you something proportional to the equation of motion of the matter field times this derivative, which will vanish on shell. Okay. There is a lot of physics encoded in these relations, and I think you should learn them. And last warning, remember that in our conventions, T00, which is related to the energy, as seen in a frame in which these are the time components, okay, of some observer, is negative. We have seen several examples of T mu nu, those that follow from the action of a scalar or an electromagnetic field, but we also said that there was a generic model of matter that was the perfect fluid model. And we had a T mu nu for that, that we found in a particular, well, first we wrote something which was non-relativistic, but which naturally accepted a 4x4 form, and then we generalized it to another metric, and applying the principle of general covariance and the minimal coupling prescription, you find that T mu nu for a perfect fluid coupled to gravity is given by this expression. So instead of theta mu nu, you have G mu nu. If you couple, now you can substitute this into the Einstein equations, well, here or rather here, and because of this chain of relations which is in this big box, consistency will demand that this is 0 on shell. So when the equations of motion of this fluid are satisfied, and in fact what one does is to accept that the equations of motion of the fluid are this. So it is a bit tautological. Okay, we can see an example of which arises in cosmology of the interplay between a non-trivial metric, the metric of a homogeneous and isotropic universe whose spatial volume depends on time. It would be a simplified model of hours if this volume expands or with time, and this perfect fluid. Okay, so for instance, consider this metric. I know if it is a solution or not, but the interesting thing is that we want to see here is how the interplay with the metric forces P and ρ to satisfy certain conditions. Okay, just these conditions are determined by this equation. It's the only thing that depends, the only dependence of this metric is on time. It is natural to think that if you have a fluid, perfect fluid, well, the pressure field will only depend on time, and that the density, the energy density field will only depend on time also. Furthermore, we can simplify the problem assuming that this vector field has this form. Okay, this means that we are choosing coordinates in which these are comoving coordinates in which we move along with the fluid. So the fluid is at rest with respect to us. The fact that it is at rest is indicated by this 0 in the spatial part. Okay, it cannot be identically 0 because you know that this has to be 1. Okay, now well, in order to write this equation explicitly, I have to compute the Christoffel symbols. So first, let us recall the definition of the Christoffel symbols. Remember that there are 3 derivatives. The last one has a minus sign. And that this index here, which is contracted first with the first 2 derivatives, but let's say that in last position, and here with the derivative, and the 2 indices that appear here, so this is symmetric and this is also symmetric. Now, okay, this is gamma mu rho, this is the Levi-Civita connection. So let's just start computing systematically the components. So first we would start with gamma TTT, and then with components TTI and so on, where I goes from 1 to 3. Okay, so first this would be GT and sigma, but this since G is diagonal, the inverse is also diagonal, and sigma has to be T as well. And then I look here and see that all these, the 3 indices that appear in this expression in brackets have to be T. And since GTT is constant, then the derivatives are 0, and this component is just 0. Okay, now let's go for the next one. Okay. Because this is diagonal, the only possibility is that this is Gij. These are derivatives with respect to t. The first and the second term add up, so I just get a factor of 2 here, but it doesn't really matter. These 2 terms are 0 because this term is off diagonal. And this term will be partial j, and it doesn't matter what is here because nothing depends on the xi's, so this component is also 0. Well, the set of components. Now let's go for the t components. Okay, now we know that this is going to be GTT, and I have t plus partial t, sorry, I GTT, but this is 0 for one reason, because it doesn't depend on xi. This is 0 because it is off diagonal, and minus partial t gti, which is also 0 because it is of the diagonal. So also 0. Next component is tij. So this would be jk. This is partial t gik plus partial I don't care because partial I, so with 0, minus partial k, and I don't care about this term either. Okay, now there is a chance that this is different from 0 because this depends on t. It is not a constant. This is a half. Now this is minus a minus 2 delta jk. And this is actually total derivative of minus a squared. So this has another minus delta ik. It's a total derivative because this depends only on t. Delta and delta give me another delta. These signs cancel. The derivative of a squared gives me a factor of 2, and what I get is delta ij a dot divided by ia, assuming that, denoted by a dot the derivatives with respect to time. So this one is different from 0. And finally, we have to check ijt. This is gtt, partial I, gjt plus partial j, git. These are 0 because there are special derivatives minus partial t gij, which will be different from 0. gtt is 1, so this is 1/2, and there is minus and the derivative of gij is minus, so this is a plus. The derivative of a squared, which is 2 times a dot delta ij. Okay, it's cancel, and this is a dot delta ij, also different from 0. And when I consider gamma ijk, I also get 0 because only spatial derivatives appear. Summarizing, typically we only write the ones that are non-vanishing. It is understood that the rest of the components vanish, and the result is that this is delta ij, and that gamma ijt is a dot delta ij. Good. Well, it would be nice to have a possibility to check the result. We can repeat the calculation, but we can run a quick test that doesn't tell you that all the components are correct, but at least it could find if some of them are wrong. And the test consists in checking that this property is satisfied. Okay, now remember that this is just a cube, which means that you can only do this test really for t. Okay, in this case you will get something different from 0, and for the spatial components you have to get 0. Okay, so is this correct? Well, the only components that you have with this t are these ones, so it will be iit, and this is a dot a delta I, which is 3 times a dot divided by a, and you can check that it is exactly the same as this. So this is correct. And about this, well, gamma mu I could be this, which is 0, and this, which is also 0. So it is correct that it is 0. Okay, now that we have run this test, we can go to the equation that we want to check, or rather the equation whose meaning we want to interpret, because we said that this equation becomes the equation of motion of the fluid. It will tell us something about the pressure and the energy density. So let us first write this equation in detail. And then it has mu rho nu t mu rho. Okay, now because this is 1 over the square root of g partial rho square root of g, we know that these two terms can be collected into a single term, which could be this one, but you still have the other one, gamma mu rho mu t mu rho. This is a bit simpler than computing this, and to simplify it a bit further, we multiply everything by the square root of g. And now we start replacing the things that we know. So we know gamma, we know square root of g, but we don't know the components of t. So first, we have to wait a bit before checking this, because we have to compute the components of t. According to the definition, this was p plus rho u nu minus p times g mu nu. G mu nu is diagonal, and this is also diagonal because only for mu and nu equal to 0, this gives you something. So t mu nu will be diagonal. Let's compute the components of the diagonal, 0, 0 or tt. Okay, this is p plus rho, and ut is 1, so you get 1 minus p, and gtt is also 1. These two terms cancel, and this is rho. So ttt is minus rho, which coincides with what I have told you happens in my conventions. Then the other components are, okay, the first term vanishes, so it's only minus p gij, and this is plus p a minus 2 delta ij. So tij is p divided by a squared with a minus delta ij. And these are all the components of the energy momentum tensor. Now let's go back to this formula here and start substituting things. So the square root of g is a cube, and we have t mu nu plus a cube, and we just said that t mu rho is diagonal, but there are no, so this could be 0, 0, but there are no gamma 0, 0, whatever components, so this has to be tij. And then the free index nu. Okay, and with tij, well, let's see. Now for nu equal to t, we have partial mu a cube t mu t, but this implies that mu has to be t. That's the only possibility, which is not vanishing. So this is what you get, plus a cube gamma ij, and the t ij, which is minus p divided by a squared delta ij. Okay, this is minus rho, and gamma ijt is here is a dot delta ij. A dot delta ij. Okay, so this is minus now total derivative of a cube times rho. Here there is another minus, and I have a cube, a4 divided by a squared, so this is a squared, a dot, and delta ij gives me 3. Right, now let me change the sign, and okay, let me do this for the moment as it is, okay, and we will find interpretation later. Let me write the other equation with nu equal to I. We have I cube d mu I, but this means that mu has to be j, and this has to be j. Nothing depends on spatial indices, so this vanishes, plus a cube I j, well, or rather j k I t j k, but gamma j k I is 0, so this equation is identically 0. It doesn't tell you anything. We only have to interpret this equation here. Remember that rho is the energy density, and clearly the volume of the spatial volume at time t is given by a q. Okay, so this you can write as the amount of energy which is contained in this volume of psi. The amount of energy which is contained in this volume of side A. A Q is just this volume, okay, and this equation you can write in this way, E plus, and you see that this is the derivative of, sorry, I forgot the factor of p here, so this is dA cube with respect to t, and p, what okay, this is just the derivative of delta v equal to p. Okay, and this is just an expression of the first law of thermodynamics, okay, for a adiabatic process, okay, how the energy changes with time. Okay, this is the only thing that changes. The changes are changes with time here, so the energy can only change with time, and the volume only changes with time, and the change in the energy is proportional to the variation of the volume times the pressure. Oops. So the kind of laws of motion that you get from this equation, the divergence of the energy momentum tensor equal to 0, really are meaningful equations. Okay, this is a very simple case. There are more complicated cases in which there are other variables at play, but I thought that this would be an example, and also a simple exercise of calculation of Christoffel symbols and so on.